Okay, we're going to take a look at a new type of gas law problem. This one is referred to as the combined gas law. So we've looked at temperature and pressure, we've looked at temperature and volume, we've looked at pressure and volume, but what happens if all three of those variables are involved? Well, that's going to change our problem just a tiny little bit. We first need to make sure that we've defined this STP. And STP stands for standard temperature and pressure. And the conditions for STP, the temperature is 273 Kelvin, which is 0 degrees Celsius, but we would use Kelvin because it's a gas law problem, so we would need our conversion to be in Kelvin. And the pressure is equal to any one of these constants that we know. So 1 atm, 101.3 kilopascals, 760 millimeters of mercury, or 760 torr. And so we just need to learn those conditions. Under those conditions, 1 mole of gas is equal to 22.4 liters. So we learned this when we learned stoichiometry, and I said these are always at STP, but we don't need to worry about STP until we get to gas laws. And lo and behold, here we are at gas laws. So if we have a problem where something like 10 centimeters cubed volume of a gas measured at 75.6 kilopascals and 60 degrees Celsius, so I'm going to make a little list, V, P, T, and V, P, T. My volume is 10 centimeters cubed. My pressure was 75.6 kPa. My temperature is 60 degrees Celsius, which plus 273 gives me 333 Kelvin. And it's corrected to correspond to the volume it would occupy, so that's what we're looking for. What is the volume that it occupies at STP? So STP, I need to know that my pressure, and it's kilopascals, so my pressure is going to be that standard 101.3 kPa, and that my temperature is going to be 273. So since I'm looking for volume, I'm going to start with volume. Look at that. So I'm going to start with my volume, which is this 10 centimeters cubed, and I have to take into account both of my variables. So I know my relationship between volume and temperature is direct. So I'm going to address them individually. So I'm going to start with temperature. My temperature is going down. If my temperature is going down, that will affect my volume by also making my volume go down. And so in that case, now I have to put 273 on top and 333 on the bottom. Temperature goes down, my volume will go down. My pressure is going from 75 to 101. My pressure is going up, so my volume must go down. So I'm looking at these individually. So if my volume must go down, I get 75.6 kPa on top and 101.3 kPa on the bottom. I multiply across, I multiply these two, I divide, and I end up with 6.1 centimeters cubed. In this case, both of my variables affected my initial volume the same way, and so I can sort of check my answer, but I can't always check my answer if what I'm doing to my conditions affects it in different ways. Let's take a look at one more. Methane is compressed in a closed 15.8 decimeter cubed container at 101.3 kilopascals. If the volume drops to 8.7 and the temperature begins at 25 and drops to 18, what will the pressure of the gas be? So again, lots of numbers, lots of variables. Let's V, P, T. I'm going to make two sets of conditions, and then I have V, P, T. And let's go through. My volume is 15.8 decimeters cubed, which is a liter. Pressure is 101.3 kilopascals. And then I'm reading along. The volume drops to 8.7 decimeters cubed. And then it goes to a new sentence. It says the temperature begins at 25, which means that's an initial condition, and then drops to 18. What will the pressure of the gas be? So this is what I'm looking for here. I need to convert to Kelvin, so before I even think about my problem, I'm going to convert it to Kelvin. 298 Kelvin, and plus 273 gives it 291 Kelvin. Pressure is what I'm looking for, so I'm going to start with that 101.3 kPa. 2 steps, 1, 2. Okay, I take a look at this and I say, okay, the first one I'm going to address is temperature. I like to just because it's direct. So my temperature is going down. If my temperature goes down, my pressure goes down. Smaller number on top, 291 K, 298 K. Now let's look at our volume. Volume is going down, which means my pressure is going up. So this is opposite. These are acting in opposition to each other. They're not supporting each other like they were in the last problem where both things were causing our units to go down. So in this case, my temperature is saying, hey, my temperature is going down, so let's make the pressure go down. Okay, so that's how that'll affect that. But then my volume is going down, which is saying, hey, let's make the pressure go up. So I'm going to treat this one separately and put the 15.8 decimeters cubed on top and the 8.7 decimeters cubed on the bottom. I go through and I solve this, 179.6 kilopascals. And unlike the other problems where I could check and say, oh yes, this is the right thing that happened, because they were acting in opposition to each other, I can't always look at my answer compared to my beginning and know if I did it right. I just need to know that I've calculated each step individually and know that that has made it be correct.